with an HCP, and I want you guys to understand these concepts very, very clearly. And if we have some problems to solve related to these concepts in our quizzes or these exams, I want you guys can do these things very, very well. And also there are several other concepts, for example, linear elasticity, linear density and also planar density. You need to understand this one also very, very well. And also this is several other concepts and you need to know that, okay? And then today we're going to talk about the imperfections in solids. So this is, we know the crystal structure determines the mechanical properties of the material, and also that is kind of idealized case scenario, because sometimes when people excuse me, when people made this material from the raw material, there are some imperfections induced during these manufacturing processes, or and originally at the very beginning, and there are some imperfections and in the solids that we got from the earth, from the nature. And so this is a reason, and we want to talk about how the imperfections influence, how these imperfections influence the mechanical properties in solids. So here is a look at this slide. The imperfections in solids, and there is no such thing as a perfect crystal, as I said, and either it is the imperfections and they were induced during manufacturing processes, or at the very beginning when we got these kind of materials from the earth, and we already have some imperfections in the solids, and we just got. So where are these imperfections? What are these imperfections? And why are they important? So this is, I told you why they are important, because they are determining the mechanical properties of the specimens, of the products you are using. So many of the important properties of materials are due to the presence of imperfections. So first we talk about the types of imperfections. There are several types. First one is a point defects. The point, you can, as the name suggests, point, that is, and different locations of point. So point defects include vacancy atoms. As the name is very, very self-explanatory. Vacancy means this some or one or some items, and they don't have items in this space. Interstitial items, also this is self-explanatory. So interstitial, there's some smaller items and were induced in the space between these bigger items. So these are substitutional items. This is also very, very self-explanatory. I'm going to talk about this in detail. And this is for point defects. And for line defects, it is a dislocation. We call this a dislocation. Line defects, as the name suggests, it means that so there is a perfection that spatially it is forming a line. And dislocations. So the area defects. Area defects, it is a bigger. You can see point is a point, and line, multiple points form a line, many lines they form an area. And so area defects include these grain boundaries. So we first talk about the point defects in these metals. Now look at it. This is a metal. We just use the 2D. So this is 2D to make our explanation more convenient. Just assume. So this is a 3D. We just look at this cross-sectional area. So the vacancy. So this is a vacancy. So here is the atoms. These are atoms here. So you can just assume for some reason this here originally we have item, but for some reason we just took it away. If we took it away, excuse me, so this is a neighboring items and will have the tendency to go closer because there is empty, and these four guys will go closer. As a result, the other neighboring these items, they will also have the tendency to come closer to this empty space. So here we can see if we draw a line here, draw a line, and we can see these lines originally perfectly if we do not have this vacancy. And these lines, they are straight line, either horizontal or vertical. But if we do have a vacancy here, so as I said, the neighboring items, they have the tendency to come closer to this location where we lose this item. So then we have these lines become distorted somehow, somewhat here. So this is a distorted plane. We call this distorted plane. If we just look at this is like the 3D, just think about the thickness into the screen. Here is this one for the horizontal line also. So this is a distorted the plane. So this is a vacancy. Second one is self-interstitial. Self-interstitial here, you can see here is contrary to these vacancies. It is extra atoms positioned between atomic size, here. So this is to see, suppose if we do not have this one, so we will have a very perfectly arranged the items. However, if we put extra atom here, so this atom, if we put it here, even though it has a very equal size of the previous of the neighboring items, but because the existence and the other neighboring items will be repelled further from this location. So we can see we see the distortion of planes, but in the opposite direction from this one. So this is self-interstitial. This is called self-interstitial. Self-interstitial means that these extra atoms, they are the same as the atoms that are existing already. Self-atoms. So this is on the contrary, opposite to self-interstitial, we have interstitial. Interstitial, that kind of interstitial means that we have some other extra atoms that are positioned in this lattice, and we have. And then we talk about the equilibrium concentration, and we suppose at some time, so this is all the atoms, they reach the state of equilibrium, and then we can calculate the equilibrium concentration. And for the point defects, equilibrium concentration varies with temperature. So this is the very, very basic fact we should know, because the temperature influence the lattice structure, influence the distance between the atoms. So we have this equation. Okay, so this is the number of defects. So this is, for example, vacancy. For vacancies here, number of defects. So this n is the number of potential defect sites. Number of potential defect sites. Number of defects. So this one can be calculated using this exp. This is parentheses. We have numerator, denominator. Numerator is activation energy. Okay, so this is lowercase k. For this is the denominator. So this is a Boltzmann constant, and this is a T is a temperature. So here is each lattice site. Okay, this is each lattice site. Each lattice site is a potential vacancy site. You can see based on each lattice site is a potential vacancy site. So the Boltzmann the constant, we have two different values, because for different these units. For here is the joule per atom multiplied by K. So here, this one, second one is EV atom per K. Can somebody tell me what is the EV? Okay, so EV is electron volts, and it's called volts, but it is the unit for energy. And so this case, EV is very, very small energy unit. It's much, much smaller than this J. And based on these two equations, you can know 1 EV equals and how many of these joules. And so I want to give you this assignment to you and to relate the EV and the joule. And I will ask you guys to come to the board next time and to write the equation that relates these two. This is EV and joule on the whiteboard. All right, so I just give you the assignment here. And then we talk measuring this activation energy. We can get this QV from the experiment. So this is experiment. And then we use this equation to calculate the NV. So measuring this. So this is the temperature. This is the temperature and defect concentration. So here, okay, this defect concentration. And we can see, so this is the defect concentration increases exponentially as this temperature increases. If we replot it, so this one is exponential dependency between this is concentration of defects and this is the temperature. And then we use the natural log, logarithmic this scale, and we will have this kind of straight line, right? So this kind of straight line. So this is hypothesis is 1 over t. This alternate is natural log nv divided by n. So this is a straight line. The slope is qv/k. Any questions so far? So both of these two figures, they are correct, as I said. So they just based upon different the scales. So this one is a linear scale, and so this one is natural logarithmic scale. Questions so far? Okay. Now then we have I'll give you an example, estimating vacancy concentration, and find the given number of vacancies in 1 cubic meter of copper at 1000 degrees C, and given conditions on density of copper, and this is ACU, atomic weight, and QV activation energy, and Na is this is Na is atoms per mole, and we use this equation, okay, Nv n this n, and so this is a 0.9, this is a 0.9 QV, and so this K is Boltzmann, this is a constant, and this equals, because this is using QV using the electron volts, and for the Boltzmann constant, and you better use the second the parameter which is written in terms of the electron volt, right? You need to use the consistent units when you do calculation. Otherwise, you will either get wrong answers, or you need to do some conversion inside of here. So here is the T, the temperature. Please know that this capital T, you need to use absolute temperature, and for which the unit is Kelvin. And what is the relationship between the degree C and the degree and the Kelvin? And you just plus the number of degree C add a number of degree C to this 273K, because 0 degree C equals 273K, right? So we have 1273K here, and so then we can get this. This is the number. So this n, right? So this n equals rho multiplied by this is the density multiply Na. Na is atoms per mole ACU. This is the mass per mole multiplied by the volume 1 cubic meter. So this equals so many sites, and then just plug in and we will get this NV. So this is the vacancies. Oh, right? Any questions so far? And so this is the basic calculation, and I want you guys to understand how to use you do not need to memorize the equation, but you need to understand it. So if I give you the similar questions, problems in the either quiz or exam, and you should be able to use this right procedure to calculate the NV here. Any questions so far? So two things I want to emphasize. First one, you need to use consistent units. If you use electrovolts as energy, and you need to use it consistently for all these parameters that have the energy unit. Second one, the temperature T, you need to use absolute temperature, and for which the unit is Kelvin. It's not degree C, not degree F. If you do not follow these instructions, and you will make mistake when you do these computations. And then we talk about solid solution. And this is solid solution, as the name suggests. We know the solution, right? We know the solution, and for example, we have a cup of water, we have a spoon of the sugar. We just put it in, and after sometimes all the sugar dissolves in the water. We have a solution, and this is a sugar water solution. And so this one, this very uh, uh, analogous situation here. So okay, so here is we call this is a solid solution. This is called a solution. So this is the items here, and we have so this is suppose we have a substitutional one. Okay, so this is a substitutional impurity item. You can see substitutional. So this guy, this here is an interstitial impurity atom, which is much smaller than the existing items here. And so because this is a small size, this guy can easily accommodate within this is a spatial. So this interstitial impurity atom, so this is substitutional impurity atom. So this is called a solid solution. This is very is analogous and to what I just told you, sugar and water. We put them together, the sugar dissolves in the water, and we have sugar water. Here we call it solid solution. Imperfection in metals. Imperfection in metals. Conditions for these substitutional solid solutions we call this as solid solution. And here is based on Professor Hume Rosary law. There are several conditions if you want to get a substitutional solid solution. So first one, the atomic radius, the atomic radius of the existing atoms and the extra atoms, the atoms you add, or it is for some reason ended in the existing atoms. So the distance, the difference between these two different radii must be less than 15%. So this is understandable. We can imagine if these two atoms they are very different from each other in size, and so they cannot have a substitutional. Okay, we can if the extra external atoms they are very small, we can have interstitial. It is interstitial one instead of this substitutional. If the extra one is very, very big, that is not definitely is not substantial. So second one, proximity in periodic table. Proximity in periodic table. That means in periodic table, these two different items, they need to be very, very close. Why it needs to be very, very close? And so we want to have similar electronegativities. So if they do not have similar electronegativities, there might be trouble. Okay, so there might be the tendency of chemical reaction, so which is bad. Chemical reaction, and then you will have the third material, which is different from the existing items and also different from the adding items. The third rule is same crystal structure for pure metals. The crystal structures we have talked about before: SC simple structure, and BCC body-centered structure, the cubic, and FCC face-centered structure, and also HCP. So this one you need to be followed. Otherwise, it is difficult and to put them together in a stable crystal structure. The fourth one is valency. What is valency? Valency means that we know valency, right? Can somebody tell me what is valency? Okay, nobody raise hands, and let me just give you some valence electrons. So what is a valence electrons? Valence electrons is electrons that are orbiting around the nucleus at the outest layer. So this is which valency electrons, and they are most important for the chemical properties of element. So all else valency, all else being equal, a metal will have a greater tendency to dissolve a metal of higher valency than one of lower valency. So what does this statement mean? It means that the metal tends to dissolve another metal of higher valency than one of lower valency. Lower valency is more stable. Higher valency is active. Right? Questions so far? So here is the application of Human-Rothery rules solid solutions. So you can see here element, atomic radius, crystal structure, electronegativity, and valence. So these are valence here. So would you predict more Al, aluminum, or silver to dissolve in zinc? Can somebody answer these questions? And you need to follow this one, right? So more zinc or aluminum in copper. And how to solve this problem? We need to come back and to see what the Hume-Rothery rules say. And they need to have similar radius. They need to have similar electronegativities. They need to have similar valency. And they need to be closer in the period. That is electronegativity. So you need to follow the rule and to determine to answer these questions. So I will give you several minutes, and because of time, and I want to, I'll ask you to do this one, and you can do this either in a team or just by yourself, and do these things after we finish today's class. By next class, at the very beginning of the class, I will cold call some students to come to the whiteboard and to tell people how they answer these questions and why. And then we talk about impurities in solids, specification of compositions. we have computations. How can we specify the specifications? The percentage, right? The percentage. And we have two. We have weight percent and we have atom percent. This is a weight percent. C1. This is mass 1, component 1, and the total mass M1 plus M2. 1 means component 1, and 2 is component 2. And without loss of generality, we just use two different components and to illustrate how we define the specifications of composition and also how we calculate them. So this multiplied by 100. So this is weight percent, atom percent, and C1, right? C1 prime. And so NM1, N is the number of moles of components, right? Number of moles of components 1. NM2 is number of moles of components 2, component 2. So this is the sum of these two guys. This is the imperfection. We saw imperfection. Then we multiply by 100. So this is, you can either use weight percent or this atom percent to denote the specification of the composition. Any questions so far? No question? So no questions. This is a composition conversion. I give you these is the equations and how to convert this from C1 to C1 prime and from C1 prime and to C1, and the same thing for C2 prime and C2. Okay? So this is equations. So C1 prime is a weight percent. C1 is a weight percent. C1 prime is the atomic percent. So they are related, but they are kind of different in terms of numbers. But I know you need to know that they are related. So you need to be very, very careful about this, and then how to do the conversions correctly. As I said, in our next class, I'm going to ask some students. I said I will cold call. I don't know whose name will be called, but I need to tell you, I will cold call. I will look at the this is a list, your name list, and then I will cold call some people's name and come to the board and to answer some questions. And not, I'm sorry, I should not say that, to help the whole class to understand some important concepts we talk about today, and do some conversion versions to illustrate to our whole class and how they handle these conversions. I hope you will like this kind of interaction with other students. I believe that this kind of interaction will enhance our learning experience and also learning productivity.